C++. Let's start with the most iconic programming language in game development, C++. Known for its speed and efficiency, C++ gives developers full control over a game's performance. Key features: low-level memory management. Developers can fine-tune every aspect of the game to optimize performance. Widely supported, used in engines like Unreal Engine and CryEngine. Object-oriented programming, OOP, makes it easier to organize and reuse code. Use case: C++ is perfect for high-performance games, especially for AAA titles that demand realism and large-scale mechanics. Notable games made with C++: The Witcher 3, Fortnite, Assassin's Creed. C#. If you ever worked with Unity, then you've probably used C#. This high-level language is popular for its simplicity and versatility. Key features: beginner-friendly, easy to learn with a clean and readable syntax. Great for scripting, ideal for gameplay mechanics, AI, and user interactions. Widely supported by Unity. Unity's documentation and community make it even easier to use. Use case: from indie games to complex 3D environments. C# is the go-to language for developers working with Unity. Notable games made with C#: Among Us, Hollow Knight. Python. Python might not be the fastest language, but it's incredibly powerful for certain aspects of game development. Its simplicity makes it a favorite for prototyping and scripting AI behavior. Key features: easy to learn, perfect for beginners starting in game development, great for AI and machine learning, often used to script complex NPC behaviors. Versatile libraries, frameworks like Pygame and Panda 3 simplify development. Use case: Python is ideal for educational games, rapid prototyping, or adding smart AI elements to existing games. Notable games made with Python: Battlefield 2, Modern, Civilization 4, AI scripting. Java. Java is a powerhouse for mobile and cross-platform games. Its write once, run anywhere philosophy allows developers to create games for multi-devices with minimal adjustments. Key features: platform independence, works seamlessly on PCs, Android, and even web platforms. Extensive libraries, frameworks like libgdx simplify game development. Garbage collection automates memory management, reducing bugs. Use case: Java is a favorite for Android game development and cross-platform objects. Notable games made with Java: Minecraft. JavaScript. For browser-based games, JavaScript is a top contender. Paired with HTML5 and libraries like Phaser.js, JavaScript makes developing web games faster and efficient. Key features: cross-platform compatibility, works on any device with a web browser, dynamic content creation, great for interactive elements in games, integration with WebGL, enables 3D graphics in browsers. Use case: JavaScript is perfect for casual and multiplayer web games, especially those with cross-device functionality. Notable games made with JavaScript: 2048. Lua. Lua is a lightweight scripting language often embedded in game engines to provide flexibility for developers. Key features: fast and efficient, lightweight and perfect for scripting game mechanics, great for mods, frequently used in popular games to extend functionality, integration with engines, works seamlessly with Love 2D and Roblox Studio. Use case: Lua is commonly used for scripting AI behaviors, in-game events, and creating mods. Notable games made with Lua: Roblox, World of Warcraft. Swift. For iOS game development, Swift is the go-to language. Apple created Swift to provide speed and safety, making it ideal for games on their platform. Key features: fast performance, optimized for iOS and macOS, modern syntax, easy to read and write, powerful frameworks, works with SpriteKit and SceneKit for game development. Use case: Swift is perfect for developers creating games for iPhones and iPads. Notable games made with Swift: Crossy Road. GDScript. GDScript is the scripting language designed specifically for Godot engine. Its simplicity and tight integration making it a favorite for indie developers. Key features: custom-made for Godot, perfectly integrated with the engine's node system, Python-like syntax, easy to learn for beginners. High-level language, ideal for scripting gameplay and UI elements. Use case: GDScript is perfect for 2D and 3D indie games developed in Godot. Notable games made with GDScript: Luck Be Around the Road. AAA game. High-budget games created by large development studios, example including The Last of Us or Halo. Alpha, an early testing phase of a game where the core mechanics are implemented but the content and polish are incomplete. Ambient inclusion, a shading technique that simulates how light interacts with objects to create realistic shadows. Animation, the process of creating movement for characters or objects in a game. API, application programming interface, tools and protocols that allow different software components to communicate, often used in game engines. Assets, visual, audio, or interactive components used in a game, such as texture, models, or sound effects. Artificial intelligence, AI, the programming of non-player characters, NPCs, to simulate human-like behavior. Backend, the part of the game that handles data management, networking, and processing behind the scenes. Beta, a later testing phase where the game is more complete but still being polished. Bellboarding, a technique where a 2D image always faces the camera to simulate a 3D object. Build, a compiled version of the game that can be played or tested. Collision detection, the process of determining when the objects in a game intersect or come into contact. Cutscene, a non-interactive cinematic sequence in a game that advances the story. Debugging, the process of identifying and fixing errors or bugs in the game code. Dialogue tree, a branch system that allows players to choose responses in conversations. Engine, the software framework used to build games like Unreal Engine, Unity, or Godot. Fog of War, a visual effect in strategy games that obscures unexplored areas. Frame rate, FPS, the number of frames displayed per second, affecting how smooth a game looks. Game loop, the core cycle of operations in a game including input processing, game logic, and rendering. GDD, game design document, a detailed plan outlining every aspect of a game. Hitbox, the invisible area around a character or object that determines collisions. HUD, a heads-up display, the on-screen interface that shows health, ammo, or other important information. Input lag, the delay between a player's action and the game's response. Instance, a unique copy of an object in a game. Isometric view, a perspective that shows a game world from a fixed angle viewpoint. Level design, the process of creating playable spaces in a game. LOD, level of detail, a technique that reduces the complexity of models as they move further from the camera. Modding, altering a game's files to create new content or mechanics. Motion capture or mocap, using real-world actors to record realistic movements for characters. Multiplayer, a mode where multiplayers can interact in the same game environment. NavMesh, navigation mesh, a tool for AI pathfinding in 3D environments. Node, a single unit in a game engine's hierarchy, often used in engines like Godot. NPC, non-player character, characters in a game controlled by AI rather than the player. Optimization, the process of improving game performance and reducing resource usage. Parallax scrolling, a technique that creates a scene of depth by moving background layers at a different speeds. Particle system, a tool to create effects like smoke, fire, or explosions. Pixel art, a graphic style where images are created with visible individual pixels. Playtesting, testing a game with real players to find issues and gather feedback. Procedural generation, creating content dynamically through algorithms often used in games like Minecraft. PvP, player versus player, a multiplayer mode where players compete against each other. Quest, a task or mission given to a player to complete. Ragdoll physics, simulating realistic character movements when they fall or collide. Ray tracing, a rendering technique for realistic lighting and shadows. Rendering, the process of generating images from game data. Respawn, reintroducing a player or NPC to the game after death. Resolution, the number of pixels displayed on the screen affecting visual quality. Rigging, the process of crafting a skeleton for a 3D model to enable animation. Sandbox, a game with open-ended exploration and player freedom, like Minecraft. Scene, a collection of objects, lights, and other elements in a game environment. Scripting, writing a code to define game behaviors and interactions. Shader, a program that controls how objects appear visually. Skybox, a 3D environment that simulates a sky or distant background. Spawn point, a designated location where players or objects appear in the game. Sprite, a 2D image used in games, often for characters or objects. Texture mapping, applying images to 3D models to give them color and detail. Tilemap, a grid-based system for creating 2D environments. Trigger, an event that occurs when a player interacts with an object or area. UI, user interface, the graphical elements players interact with, like menus or buttons. Vertex, a point in a 3D space used to define the shape of a model. Viewport, the visible area of the game displayed on the screen. Unreal Engine. Let's start with the powerhouse of game development, Unreal Engine. Known for its stunning graphics and versatility, Unreal Engine is a favorite among AAA studios and indie developers alike. Key features: photorealistic graphics, powered by Unreal's cutting-edge rendering tools, including Lumen and Nanite for dynamic lighting and high-detailed models. Blueprint visual scripting allows developers to create gameplay mechanics without writing code. Wide performance support. From consoles to mobile devices, Unreal can handle it all. Use case: Unreal Engine is perfect for creating high-performance games with realistic visuals, like first-person shooters, open-world RPGs, and cinematic adventures. Notable games made with Unreal Engine: Fortnite, The Witcher 3, Hellblade. Unity. If Unreal is the powerhouse, Unity is the workhorse of game development, known for its versatility and ease of use. Unity is a favorite among indie developers and small studios. Key features: 2D and 3D support, equally capable of creating simple platformers or immersive 3D worlds. Extensive asset store, thousands of pre-made assets to speed up development. C# scripting, a beginner-friendly, yet powerful programming language. Use case: Unity is great for games of all sizes, from mobile hits to console experiences. It's also widely used for VR and AR projects. Notable games made with Unity: Among Us, Hollow Knight, Cuphead. Godot Engine. Godot is an open-source game engine that's been gained popularity for its flexibility and simplicity. Designed for developers of all levels, it's lightweight and highly customizable. Key features: node-based architecture makes it easy to organize game elements. GDScript, a Python-like scripting language tailored for game development. 2D first approach, exceptional tools for creating 2D games, though its 3D capabilities are improving rapidly. Use case: Godot is perfect for indie developers creating 2D games, like platformers or puzzle games. It's also free, with no license fees. Notable games made with Godot: Kingdoms of the Dam, upcoming, Luckby Around the Road. CryEngine. CryEngine is renowned for its breathtaking visuals and advanced rendering capabilities. Developed by Crytek, this engine is ideal for developers who want to push the boundaries of realism. Key features: real-time lighting and shadows, exceptional graphics for immersive environments. Advanced Physics Engine, known for its realistic, destructible environments. Flow Graphic Editor, a visual scripting tool for gameplay mechanics. Use case: CryEngine is best for FPS games and other projects that prioritize cutting-edge graphics. Notable games made with CryEngine: Crisis Series, Hunt Showdown. RPG Maker. RPG Maker is a specialized engine for creating 2D role-playing games. RPG. It's incredibly beginner-friendly and doesn't require any programming knowledge. Key features: drag-and-drop interface, perfect for non-programmers. Built-in assets include character sprites, tilesets, and music. Event system simplifies the creation of dialogues, battles, and cutscenes. Use case: RPG Maker is ideal for developers focused on storytelling and classic RPG gameplay. Notable games made with RPG Maker: To the Moon, Lisa the Painful, One Shot. GameMaker Studio. GameMaker Studio is another beginner-friendly engine, but it's far more versatile than you might think. While it excels at 2D games, it's also capable of producing polished, high-quality projects. Key features: drag-and-drop functionality, great for newcomers. GMR, GameMaker Language, a scripting language for more advanced features. Cross-platform support, easily export games to PC, consoles, and mobile devices. Use case: GameMaker is perfect for 2D games like platformers, shooters, and roguelikes. Notable games made with GameMaker Studio: Undertale, Hyper Light Drifter. Frostbite Engine, developed by EA. Frostbite is a proprietary engine known for its realistic physics and visual fidelity. It's used exclusively by EA's studio for their flagship games. Key features: destruction mechanics, incredible physics for destructible environments, seamless transitions between cutscenes and gameplay, integrated audio tools, advanced sound design capabilities. Use case: Frostbite is best for large-scale AAA games, especially FPS and sports titles. Notable games made with Frostbite: Battlefield series, FIFA series. Source Engine. Source Engine, developed by Valve, is known for powering some of the most iconic games in history. The Origin. It's still beloved for its modern community and robust physics. Key features: advanced physics engine, enables realistic object interactions. Modding support. Games like Garry's Mod shows the engine's creative potential. VR support, powering games like Half-Life Alyx. Use case: Source Engine is perfect for FPS games and projects that focus on environmental storytelling. Notable games made with Source Engine: Half-Life 2, Portal 2, CSGO. Constructor. Constructor is a 2D game engine designed for simplicity and rapid prototyping. It's a no-code platform, making it perfect for beginners. Key features: event-based logic, create gameplay without writing code, browser-based, build and test games directly in a web browser. export options, publish to mobile, PC, and even HTML5. Use case: Constructor is ideal for small, creative projects and game jams. Notable games made with Constructor: The Next Penelope, Cosmosis. Panda 3D. Panda 3D is an open source engine with a focus on Python scripting, making it ideal for developers interested in combining simplicity with power. Key features: Python-based, easy scripting for beginners, 3D rendering tools, suitable for small to medium 3D projects, cross-platform support, works on Windows, macOS, and Linux. Use case: Panda 3 is great for indie developers creating 3D games or simulations. Notable games made with Panda 3D: Pirates of the Caribbean Online. Game mechanics. Game mechanics are the rules and systems that define how a game works. These are the core interactions players have with the game, such as moving characters, collecting items, or solving puzzles. Example: in Super Mario Bros., mechanics including jumping, running, and collecting coins. These simple systems combine to create a fun and engaging experience. Why it matters? Mechanics form the foundation of gameplay, ensuring that every action feels purposeful and rewarding. Game loop. A gameplay loop is the circle of actions players repeat throughout the game. For example, in Minecraft, the loop might involve gathering resources, crafting tools, and building structures. Why it matters? A well-designed game loop keeps players engaged by creating a satisfying rhythm of challenges and rewards. Core gameplay. The core gameplay refers to the primary activity players engage in. It's the essence of the game's experience. Example: in a racing game, the core gameplay is driving and competing against opponents. Everything else, upgrades, storylines, or multiplayer, is secondary to this central activity. Why it matters? Focusing on strong core gameplay ensures the game delivers on its main promise to the player. Game balance. Game balance is the process of ensuring fairness and challenge in a game. It's about making sure no character, weapon, or strategy is overpowered or too weak. Example: in Overwatch, game balance involves tweaking a character's abilities to maintain fair competition across all play styles. Why it matters? Balanced games are more enjoyable, competitive, and satisfying for players. Progression system. A progression system allows players to grow and improve as they play. This could include leveling up, unlock new abilities, or earning better gear. Example: in The Witcher 3, players level up Geralt by gaining experience points and unlocking new skills. Why it matters? Progression gives players a sense of achievements and motivation to keep playing. Replayability. Replayability refers to a game's ability to remain fun even after being completed. This can be achieved through multiple ends, procedurally generated levels, or unlockable content. Example: Hades has high replayability thanks to its recurlog mechanics, where each run feels unique. Why it matters? Replayable games provide more value to players, giving them engage for long periods. Immersion. Immersion is the feeling of being fully absorbed in a game's world. It's achieved through strong storytelling, detailed visuals, and interactive environments. Example: The Elder Scrolls V, Skyrim create immersion with its expansive open world, dynamic NPCs, and atmospheric music. Why it matters? Immersion enhances the emotional connection players have with the game, making it more memorable. Risk and reward. This concept involves creating situations where players must weigh potential benefits against possible losses. Example: in Dark Souls, risking a dangerous path may lead to a valuable loot, but could also result in death. Why it matters? Risk and reward add tension and excitement, encouraging strategic decision-making. Player agency. Player agency is the sense of control players have over their actions and the game's outcomes. Example: in Mass Effect, players make choices that influence the story's direction and ending. Why it matters? When players feel their actions matter, they become more invested in the game. Pacing. Pacing is the rhythm of a game's event, balancing moment of actions, explorations, and rest. Example, The Last of Us uses quick moments between battles to build tension and emotional depth. Why it matters? Good pacing keeps players engaged without overwhelming or boring them. Level design. Level design refers to the process of creating the environments and stages that the players explore and interact with. This includes the layout, obstacles, enemy placement, and rewards within each level. Example, in Super Mario Bros., the placement of blocks, enemies, and platformers in each level ensures a balance between challenge and fun. Why it matters? A well-designed level guides players naturally, teaching mechanics while providing an engaging experience. Feedback loop. A feedback loop is the system of rewards and punishments that encourage or discourage certain player behaviors. Example, in Call of Duty, players are rewarded with experience points and unlockable gear for getting kills, encouraging aggressive gameplay. Why it matters? Feedback loops help shape the way players interact with the game, ensuring constant engagement. Game feel often refers as tactile and visual feedback that makes player actions feel satisfying. This includes responsive controls, animation, and sound effects. Example, in Celeste, the thigh control and visual feedback make every jump feel precise and rewarding. Why it matters? Good game feel makes gameplay intuitive and enjoyable, keeping players engaged. Difficulty curve. The difficulty curve is the gradual increase in challenge as the player progresses through the game. It ensures the game starts easily but becomes more difficult as players master mechanics. Example, in Portal, early levels introduce basic mechanics, while later puzzles combine multiple mechanics for increased complexity. Why it matters? A small difficulty curve keeps players motivated without overwhelming them. Flow state. Flow state occurs when players are fully immersed in the game, balancing challenge and skill. It's the sweet spot where the game feels neither too easy nor too hard. Example, in Tetris, as the speed of failing blocks increases, players remain focused and engaged in maintaining their lines. Why it matters? Achieving flow state keeps players in the zone, making gameplay more rewarding and addictive. Emergent gameplay. Emergent gameplay happens when players use game mechanics in unexpected ways to create unique experiences. Example, in The Legend of Zelda Breath of the Wild, players combine physics, weather, and tools to solve puzzles in creative ways. Why it matters? Emergent gameplay gives players freedom and encourages experimentation, enhancing replayability. Game economy. The game economy refers to the system of resources, currencies, and rewards that players earn and spend within the game. Example, in Animal Crossing, players collect bells to buy furniture, clothing, and expand their homes. Why it matters? A well-balanced economy keeps players engaged by providing meaningful goals and rewards. Affordance. Affordance refers to how easily a player can understand what actions are possible within the game environment. Example, in The Witness, glowing plans and pathways subtly guide players toward puzzles without explicit instructions. Why it matters? Clear affordance reduces player frustration and ensures smooth gameplay. RNG, Random Number Generator. RNG refers to the randomness built into a game to create unpredictability. It's used for loot drops, enemy behaviors, or environmental changes. Example, in Diablo 3, loot drops are randomized, making every run feel unique. Why it matters? RNG adds variety and replayability, but must be balanced to avoid frustration. Tutorialization. Tutorialization is the method of teaching players how to play the game. It can include explicit tutorials, in-gameplay hints, or subtle guidance through level design. Example, in Hollow Knight, environmental clues and enemy placement teach players combat mechanics without a text tutorial. Why it matters? A well-designed tutorial ensures players understand the game without feeling overwhelmed. Reward system. Rewards can be incentives for players to continue playing. Rewards can be tangible, like loot or upgrades, or intangible, like a sense of achievement. Example, in Destiny 2, completing raids rewards players with powerful gear and bragging rights. Why it matters? Rewards drive player motivation and keep them coming back for more. Sandbox. A sandbox is a game structure where players are free to explore and interact with the world without a predefined path or objective. Example, in Minecraft, players can build, mine, and create at their own pace without specific goals. Why it matters? Sandbox games encourage creativity and exploration, offering a high personalized experience. Dynamic Difficulty Adjustment (DDA). DDA is a system that adjusts the game's difficulty in real time based on the player's performance. Example, in Resident Evil 4, enemy behavior and resources change depending on how well the player is doing. Why it matters? DDA ensures the game remains challenging but not frustrating, accommodating players of varying skill levels. Narrative Design. Narrative design involves crafting the story, dialogue, and the world-building elements that drive a game's plot. Example, in The Last of Us, narrative design integrates gameplay with emotional storytelling to create cohesive experience. Why it matters? Strong narrative design enhances immersion and emotional connection with the game. Procedural generation. Procedural generation uses algorithms to create game content dynamically, such as levels, maps, or enemies. Example, in No Man's Sky, entire planets and ecosystems are procedurally generated, creating a vast, unique universe. Why it matters? Procedural generation increases variety and replayability, especially in large-scale games. Jumping. Jumping is the foundation of nearly every platformer. It's the simplest action, yet one of the most impactful. How it works? Players press a button to prepare the character upward, with gravity pulling them back down. Advanced mechanics like double jumps or variable height jumps add variety. Example, in Super Mario Bros., jumping is used to overcome obstacles, defeat enemies, and collect power-ups. Why it matters? Jumping is versatile and intuitive, making it the cornerstone of platformer gameplay. Double jump. Double jumping adds an extra layer of flexibility, allowing players to change direction or recover from mistakes. How it works? After the initial jump, players can jump again mid-air to gain additional height or distance. Example, in Halo Knight, the double jump is a late-game ability that opens up new areas for exploration. Why it matters? It enhances mobility and creates opportunities for creative level design. Wall jumping. Wall jumping is a mechanic that gives players the ability to bounce off walls to reach new heights. How it works? When a character touches a wall, they can jump off it in the opposite direction, often requiring precise timing. Example, in Celeste, wall jumping is a critical mechanic for navigating challenging vertical levels. Why it matters? Wall jumping adds complexity to movement and rewards skilled players. Dash. The dash mechanic provides a burst of speed, often used for evasion, crossing gaps, or attacking enemies. How it works? Players trigger a quick horizontal or diagonal movement, often with a cooldown or limited uses. Example, in Ori and the Blind Forest, dashing allows players to reach distant platforms. Why it matters? It increases the pace of gameplay and introduces new strategic possibilities. Climbing. Climbing mechanics allow players to scale walls or objects, expanding vertical exploration. How it works? Players can grab a climbable surface and move vertically or horizontally. Stamina or time limits often add challenge. Example, in Celeste, climbing is central to the game's mechanics, with the stamina bar adding tension to each climb. Why it matters? Climbing encourages exploration and adds depth to level design. Grappling hook. The grappling hook is a mechanic that lets players swing across gaps or pull themselves towards a specific point. How it works? Players aim at a target and shoot a tether, which either pushes them forward or allows them to swing. Example, in Axiom Verge 2, the grappling hook is used to navigate large open areas. Why it matters? It introduces dynamic movement and puzzle-solving opportunities. Sliding. Sliding is a mechanic where players duck and move quickly under obstacles or through narrow spaces. How it works? While running, players can press a button to initiate a slide. Some games combine sliding with a combat or traversal. Example, in Mega Man X, sliding is essential for dodging attacks and accessing hidden areas. Why it matters? Sliding increases the pace and variety of movement, adding flow to gameplay. Swing platforms. Swing platforms add a timed change to platforms, requiring players to jump at the right movement. How it works? Platforms move in arcs, either side to side or up and down, creating dynamic hazards. Example, in Donkey Kong Country, swing ropes and vines are key to progression. Why it matters? These platforms add rhythm and timing challenges to levels. Wall running. Wall running lets players traverse walls horizontally for short distances. How it works? Players sprint toward a wall and automatically stick to it, running until momentum or time runs out. Example, in Mirror's Edge, wall running is essential for navigating the game's urban environments. Why it matters? It combines speed and skill, creating exhilarating traversal moments. Boost pads. Boost pads provide an instant speed increase, often used to cross large gaps or avoid hurdles. How it works? When a character steps on a boost pad, they are pulled forward or upward. Example, in Sonic the Hedgehog, boost pads emphasize speed and create thrilling sequences. Why it matters? Boost pads keep the pace existing and encourage fast, fluid movement. Glide. Gliding allows players to float through the air, extending their jump distance. How it works? After jumping, players can activate a glide mechanic to descend slowly or travel further horizontally. Example, in the Spyro the Dragon, gliding is essential for reaching faraway platforms. Why it matters? Gliding adds an element of strategy to platforming, encouraging precision. Transformations. Some platformers feature mechanics where the player character can transform into different shapes or abilities to overcome obstacles. How it works? Players switch between forms, each with unique mechanics such as flying, swimming, or shrinking. Example, in Shantae, Have Genie Hero, transformations allow access to hidden areas and solve puzzles. Why it matters? Transformations keep gameplay fresh and open up creative level design opportunities. Concept phase. This is where it all begins, the concept phase. Here, the game's core idea is born. Developers brainstorm unique concepts, create a rough outline, and define the game's target audience and genre. What happens? Initial brainstorming sessions, writing a game concept document, GCD, identifying the game's unique selling points, USPs. Key players, game designers, creative directors, and producers. Why it matters? This phase sets the foundation for the entire project. A strong concept ensures the team has a clear vision to build on. Pre-production phase. Pre-production is where the blueprint for the game is created. It's about planning and preparing before any major development begins. What happens? Writing the game design document, GDD, which outlines gameplay, mechanics, and story. Prototyping key mechanics to test feasibility. Building a small vertical slice, a fully playable mini version of the game. Creating concept art for characters, environments, and assets. Key players, designers, artists, and programmers. Why it matters? Pre-production minimizes the risks by identifying challenges early and ensuring the team is aligned on the project's direction. Production phase. This is the heart of game development. The production phase is where the bulk of the game is built, including coding, designing levels, creating assets, and recording audios. What happens? Developing the core mechanics and gameplay systems, building levels, characters, and environments, writing and recording voiceovers and sound effects, implementing animations and visual effects, regular playtesting to refine mechanics and fix bugs. Key players, programmers, level designers, animators, sound designers, and QA testers. Why it matters? This phase transforms ideas into a playable game. Collaboration and iteration are critical to ensure the game meets the vision set during pre-production. Alpha phase. In the alpha phase, the game is mostly complete but still rough around the edges. This stage focuses on testing and refining. What happens? Internal playtesting to identify bugs and balance issues, adding placeholders assets for missing elements, ensuring core features and mechanics are functional. Key players, QA tester, programmers, and designers. Why it matters? The alpha phase ensures the game's foundation is solid, paving the way for further polish. Beta phase. The beta phase is when the game feels like a near-complete product. Focus shifts to polish and the gathering feedback from external testers. What happens? Fixing bugs and optimization performance. Conducting closed or open beta testing with real players. Gathering feedback to refine gameplay and address overlooked issues. Key players, QA teams, community managers, and developers. Why it matters? Beta testing provides valuable insights from real players, helping to refine the game before launch. Gold phase. The gold phase marks the completion of development. The game is ready to ship. What happens? Final bug fixes and quality assurance checks, preparing the game for distribution, digital and physical copies, creating market materials and trailers. Key players, producers, marketing teams, and developers. Why it matters? This phase ensures the game is polished and ready to reach its audience. Finally, post-launch phase. The work doesn't stop after launch. Post-launch support ensures the game stays relevant and engaging for players. What happens? Releasing patches and updates to fix issues or improve features, adding downloadable content, DLC or expansions, engaging with the community to gather feedback and build loyalty. Key players, community managers, live servers teams, and developers. Why it matters? Post-launch support extends the game's lifespan and keeps players invested. Realism. Realism aims to recreate the real world as accurately as possible. It's often used in AAA games that serve for photorealistic graphics. Key features, detailed textures, lighting and physics. Characters, environments, and objects resemble their real-life counterparts. Heavy use of advanced rendering techniques like ray tracing. Example: The Last of Us Part 2, Red Dead Redemption 2, Call of Duty Modern Warfare. Why it matters? Realism immerses players by making them feel like they are part of a lifelike world, enhancing emotional and relative depth. Pixel art. Pixel art is a retro-inspired style that uses small, blocky pixels to create images. It's widely popular among indie developers. Key features: minimalistic, yet expressive visuals, often evokes nostalgia for early gaming eras. Limited resolution and color palettes are used creatively. Example: Stardew Valley, Celeste, Undertale. Why it matters? Pixel art provides that the games don't need high-end graphics to tell compelling stories and deliver fun gameplay. Cell shading. Cell shading is a stylized art technique that mimics the look of hand-drawn cartoons or anime. Key features: bold outlines and flat shading, vibrant colors, often gives the game a comic book or animated feel. Example: The Legend of Zelda, The Wind Waker, Borderlands, Genshin Impact. Why it matters? Cell shading creates a timeless visual appeal, standing out from photorealistic games. Low poly. Low poly art uses a minimum number of polygons to create characters and environments, resulting in a clean and simple aesthetic. Key features: geometric shapes with flat colors or basic textures, often used in mobile or indie games to reduce hardware requirements, can create a unique and charming style despite its simplicity. Example: Monument Valley, Astroneer, Superhot. Why it matters? Low poly art is both accessible for developers and visually striking when executed well. Hand-drawn 2D art. hand-drawn art styles features visuals that look like they've been painted or scratched by hand. Key features: rich, detailed animations, often uses a painterly aesthetic or scratch-like line work, gives games a unique example, Cuphead, Halo Knight. White matters: hand-drawn art brings a human touch to games, making them feel like living works of art. Minimalism. Minimalism focuses on simplicity, using clean shapes and limited colors to convey visual information. Key features: simple, uncluttered visuals, focuses on gameplay and functionality over detailed aesthetics, often paired with calming or abstract experiences. Example: Thomas Was Alone, Limbo. White matters: minimalism strips games down to their core, delivering powerful emotional or thematic messages. Photorealistic fantasy. Photorealistic fantasy blends realistic graphics with imaginative, otherworldly designs. Key features: high detailed environments with fantastical elements, combines realism with magic, myth, or science fiction influences, heavy use of visual effects like particle systems and dynamic lighting. Example: Elden Ring, Horizon Zero Dawn, Final Fantasy XV. White matters: this style creates believable yet awe-inspiring worlds that feel larger than life. Retro 3D. Retro 3D mimics the low-resolution polygonal graphics for early 3D games from the 1990s. Key features: blocky characters and environments, low-res textures, and limited animations frames evoke nostalgia for early 3D console generations. Example: Dusk, A Hut in Time, Tonic. White matters: retro 3D appeals to players who grow up with early 3D games, blending nostalgia with modern design sensibilities. Abstract art. Abstract art abandons realism entirely, focusing on unique shapes, colors, and patterns to create surreal experiences. Key features: unconventional visuals that challenge traditional game aesthetics, often used in puzzle or experimental games, prioritizes atmosphere and mood over clarity. Example: Rise Infinite, Thumber, Antichamber. White matters: abstract art styles push the boundaries of what games can look like, offering players something truly unique. Isometric art. Isometric art presents the game world from a fixed angle perspective, giving the illusion of depth in 2D or 3D spaces. Key features: static camera angle, often at 45-degree tilt, highly detailed environments designed for strategic gameplay, common in RPGs, strategy, and simulation games. Example: Diablo 3, Hades, Stardew Valley. White matters: isometric art provides a clear view of gameplay areas, balancing style and functionality. Leveling up. Leveling up is the core progression system in most RPGs. It's how players grow stronger and unlock new abilities. How it works? Players gain experience points, XP, by completing quests, defeating enemies, or exploring. Reaching a certain XP threshold increases the character's levels, improving states like health, attack, or defense. Some games also offer skill points to customize a character's abilities. Example: The Elder Scrolls V, Skyrim, Final Fantasy. White matters: leveling up creates a rewarding sense of growth, giving players a tangible way to see their progress. Skill trees. Skill trees allow players to specialize their characters by unlocking abilities or perks in a structured system. How it works? Players earn skill points, typically though leveling up. Points are spent on abilities arranged in branching paths or categories, such as combat, magic, or CF. Choices are often irreversible, adding weight to player decisions. Example: World of Warcraft, Cyberpunk 2077. White matters: skill trees provide depth and reliability, allowing players to customize their characters to suit their playstyles. Inventory management. RPGs often include inventory systems where players manage their gear, items, and resources. How it works? Players collect items like weapons, potions, and crafting materials. Limited inventory space or raid systems force players to make strategic decisions about what to carry. Inventory systems often include storing, upgrading, and organizing features. Example: The Witcher 3, Dark Souls. White Matters: managing inventory adds a layer of strategy and realism, especially in survival-focused RPGs. Quest systems. Quests are the backbone of RPGs storytelling, guiding players through the world and its narrative. How it works? Quests are divided into main, side, and optional objectives. Objectives include tasks like defeating enemies, solving puzzles, or collecting items. Quests often feature branching outcomes based on players' choices. Example: Massive Effect, The Witcher 3. White Matters: quests give players purpose, immersing them in the game's story and world. Dialogue systems. Dialogue systems allow players to interact with NPCs, shaping the story and relationships. How it works? Players choose responses from a list of dialogue options. Choices can influence character relationships, unlock quests, or alert the game's ending. Some systems include morality or reputation mechanics that track player decisions. Example: The Outer Worlds, Fallout New Vegas. White Matters: dialogue systems create a sense of agency, allowing players to influence the story in meaningful ways. Turn-based combat. Turn-based combat is a classic RPG mechanic where players and enemies take turns making moves. How it works? Players select action for their party, such as attacking, using magic, or defending. Combat often include mechanics like initiative, cooldowns, or action points. Strategy and planning are essential for success. Example: Final Fantasy VII Original Sin 2. White Matters: turn-based combat emphasizes strategy and allows players to think critically about each move. Open world exploration. Many RPGs features expansive open worlds, encouraging players to explore at their own pace. How it works? Worlds are filled with landmarks, hidden treasures, and dynamic events. Exploration is often tied to progression, unlocking new areas or abilities. Some games including fast travel system for convenience. Example: The Legend of Zelda Horizon Zero Dawn. White Matters: open world exploration fosters a sense of freedom and discovery, immersing players in the game's universe. Crafting system. Crafting allows players to create items, weapons, or gear using collected materials. How it works? Players gather resources through exploration or combat. Recipes or blueprints dictate the materials needed to craft specific items. Advanced crafting systems include item upgrades or enchantments. Example: The Witcher 3, Minecraft. White Matters: crafting adds depth to gameplay, rewarding exploration and resource management. Character classes. Classes defines a character's ability, strength, and weakness, shaping how they interact with the game. How it works? Players choose a class, such as warrior, mage, or rogue, at the start of the game. Classes dictate available skills, weapons, and playstyles. Some games allow multi-classing for added flexibility. Example: World of Warcraft, Dark Souls. White Matters: classes encourage diverse playstyles and team dynamics, making each playthrough unique. Morality systems. Morality systems track the ethical choices players make, influencing the game story and world. How it works? Choices are categorized as good, evil, or neutral. NPCs and factions react differently based on the player's morality. Some games feature multiple ends tied to morality. Example: Massive Effect, The Outer Worlds. White Matters: morality systems deepen player immersion, making their decisions feel impactful. Pathfinding. Pathfinding is the AI's ability to navigate the game world intelligently, finding the best route to reach a destination. How it works? Algorithms like A* calculate the shortest path from a point A to point B. AI considers obstacles, terrain, and dynamic elements like moving platforms or doors. Advanced systems adapt paths in real time based on player actions or environmental changes. Example: The Legend of Zelda, Garden Movement. Halo, Enemy Positioning. White Matters: Pathfinding ensures NPCs moving realistically, creating immersive and challenging gameplay. Enemy AI. Enemy AI dictates how opponents react to the player, from basic attacks to complex strategies. How it works? Behavior trees and finite state machines (FSM) govern enemy actions like patrolling, attacking, or fleeing. Difficulty scaling adjusts enemy accuracy, aggression, or tactics. Some AI learns from player behavior, adapting to counter their strategies. Example: Dark Souls, boss pattern, Metal Gear Solid, stealth detection. Why it matters? Smart enemy AI keeps players engaged by offering dynamic and varied combat challenges. NPC interaction. NPC interaction AI enables characters to respond behaviorally to player choices and actions. How it works? Dialogue systems use branching path or procedural generation to create conversations. NPCs track relationships, reaction differently based on player behavior. Advanced AI models simulate emotions or intentions. Example: Massive Effect, dialogue choices, The Elder Scrolls V, follower behaviors. Why it matters? Realistic NPCs deepen immersion and make the game world feel alive. Adaptive difficulty. Adaptive difficulty AI adjusts the game's challenge based on the player's performance. How it works? System track player success, failure, or time taken to complete objectives. AI modifies enemy health, accuracy, or spawn rates to balance the experience. Some games subtly adjust difficulty to avoid frustrating or boring players. Example: Resident Evil 4, Left 4 Dead. Why it matters? Adaptive difficulty ensures a balanced and enjoyable experience for players of all skill levels. Procedural generation. AI-driven procedural generation creates content dynamically, such as levels, environments, or quests. How it works? Algorithms use seeds to generate unique layouts, ensuring no two playthroughs are the same. AI balances randomness with structure to maintain gameplay quality. Example: No Man's Sky, planets, raids, dungeons. What matters? Procedural generation adds variety and replayability, making every session feel fresh. Stealth detection. Stealth AI determines how enemies detect and respond to players attempting to stay hidden. How it works? Vision cones and sound detection simulate realistic awareness. AI prioritizes actions based on previous threats, like investigating noises or searching hidden spots. Some systems include alert levels, where enemy coordinate responses. Example: Splinter Cell, Hitman. Why it matters? Stealth detection creates tense and strategic gameplay, rewarding careful planning. Squad AI. Squad AI coordinates group behaviors, allowing NPCs to work together in combat or exploration. How it works? AI communicates rules and tactics like flanking, conveying, or suppressing fire. Leader-follower dynamics assign commands and distribute tasks. Adaptive tactics change based on player actions. Example: Halo, enemy groups. Why it matters? Squad AI adds complexity and realism to encounters, making them feel organic. Dynamic storytelling. Dynamic storytelling AI adjusts the narrative based on player choices and in-game events. How it works? Systems track player decisions and relationships with NPCs. Procedural narrative generation creates unique outcomes or quest lines. Some AI uses machine learning to craft personalized stories. Example: Detroit Become Human, The Outer Worlds. What matters? Dynamic storytelling creates a personalized experience, increasing replayability and emotional engagement. Companion AI. Companion AI controls allied NPCs, helping players during combat or exploration. How it works? AI evaluates players' actions and provides support, like healing or attacking enemies. Context-sensitive behaviors ensure companions respond appropriately to the environment. Advanced systems allow players to issue commands or customize AI properties. Example, The Last of Us, LA. White Matters, smart companions enhance gameplay by providing assistance without becoming a burden. AI learning systems. Some games feature AI that learns from the player's actions, creating unique challenges over time. How it works? Machine learning algorithms analyze player behavior. AI adapts strategies, counters repetitive tactics, or increases difficulty. Example, Middle-earth, Shadow of Mordor, Nemesis system. White Matters, learning AI makes every encounter dynamic, ensuring no two playthroughs are identical. Action. Action games are all about fast-paced gameplay and quick reflexes. They focus on challenges like combat, platforming, or dodging obstacles. Key features: instant, skill-based gameplay, minimal downtime, keeping players engaged, emphasizes on physical challenges. Example, Hades, Tomb Raider. White Matters, action games test players' reflexes and decision-making skills, delivering adrenaline-pumping experiences. Adventure. Adventure games emphasize exploration, story, and problem-solving over action. Key features: rich narratives with memorable characters, puzzle solving and environmental interactions, exploration-focused gameplay. Example, Life is Strange. White Matters, adventure games immerse players in captivating stories and imaginative worlds. Role-playing games, RPGs. RPGs are all about character progression, decision-making, and immersive worlds. Key features: deep customization options for characters and abilities, expansive worlds with quests and side missions, molarity and decision-based storytelling. Example, The Witcher 3. White Matters, RPGs give players a sense of agency and long-term investments in their journey. Shooter. Shooter games focus on ranged combat, testing players' aim and strategy. Key features: first-person or third-person perspectives, a variety of weapons and combat scenarios, competitive multiplayer or narrative-driven campaigns. Example, Call of Duty. White Matters, shooters are perfect for adrenaline junkies who love fast-paced, tactical gameplay. Platformer. Platformers challenge players with jumping, climbing, and navigating obstacles. Key features: precision movement and timing, levels filled with hazard and collectibles, often use 2D or side-scrolling perspectives. Example, Super Mario. White Matters, platformer test player skills while delivering nostalgic and charming gameplay. Puzzle. Puzzle games challenge players' logic, strategy, and problem-solving skills. Key features: diverse puzzles ranging from math problems to pattern recognition, often minimalistic in design, focusing on mechanics, gradual increase in difficulty. Example, The Witness. White Matters, puzzle games simulate the brain, offering a rewarding sense of accomplishment. Strategy. Strategy games require careful planning and resource management to achieve victory. Key features: turn-based or real-time gameplay, focus on tactics, economy, and unit control, complex systems that reward long-term thinking. Example, StarCraft 2. White Matters, strategy games challenge the mind, rewarding patience and critical thinking. Simulation. Simulation games mimic real-world activities or systems with high levels of detail. Key features: focus on realism or authentic experiences, open-ended gameplay with no strict objectives, often sandbox style with deep mechanics. Example, Microsoft Flight Simulator. White Matters, simulation games let players live out fantasies or master complex systems. Fighting. Fighting games pit players against each other in one-on-one or group battles. Key features: combo-based combat systems, competitive multiplayer modes, unique characters with distinct fighting styles. Example, Super Smash Bros. White Matters, fighting games are a staple of competitive gaming, testing reflexes and strategy. Horror. Horror games focus on creating fear and tension, often blending relative and survival mechanics. Key features: atmospheric environments with eerie sound design, limited resources and vulnerable characters, psychological or supernatural themes. Example, Resident Evil 2. White matters, horror games evoke strong emotions, delivering unforgettable and suspenseful experiences. Survival games challenge players to manage resources and endure harsh conditions. Key features: crafting, scavenging, and base building mechanics. Open world exploration often includes permadeath or high-stakes challenges. Example, The Forest. White matters, survival games test resilience and resourcefulness, creating immersive and challenging experiences. Sandbox games give players unstructured freedom to explore, create, and experiment. Key features: open-ended gameplay with no strict objectives. Tools for building, crafting, or modifying the world encourages player creativity. Example, Minecraft. White matters, sandbox games allow players to express their creativity and make the game their own. Aiming and shooting. At the core of every FPS game is the aiming and shooting mechanic. It's all about precision, timing, and mastering your weapon. How it works? Players use a rectangle or crosshair to aim at targets. Weapons have unique states like damage, rate of fire, and accuracy. Advanced games include recoil patterns and bullet drop for realism. Example, CSGO. White matters, aiming and shooting are the foundation of FPS gameplay, rewarding skill and quick reflexes. Reloading adds a layer of strategy to combat, forcing players to manage their ammo during intense firefights. How it works? Each weapon has a magazine size, requiring reloading when it's empty. Some games allow tactical reloading, where unused bullets are saved. Reward animation can be interrupted, adding a risk-reward dynamic. Example, Battlefield. White matters, reloading creates a moment vulnerability, encouraging smart positioning and timing. Movement mechanics. Movement in FPS games is more than just walking. It's a tactical tool for survival and strategy. Key types of movements: sprint, covers ground quick but limits actions like shooting. Crouch, reduces visibility and increases accuracy. Slide, dive, quick evasive maneuvers to dodge enemy fire. Jumping, used to traverse obstacles or outmaneuver opponents. Example, Overwatch. White matters, dynamic movement keeps gameplay fluid and adds depth to combat encounters. Health and armor systems. Health and armor systems determine how much damage a player can take before being eliminated. How it works? Players start with a base health value, which decreases when hit. Armor absorbs a percentage of damage before health is affected. Some games including health recognition, while others are medicates or health stations. Example, Fortnite. What matters? These systems balance survivability, rewarding tactical play and resource management. Weapon variety. Weapon variety ensures every playstyle is catered to, from long-range snipers to close-quarter shotguns. Categories: assault rifles, versatile for medium-range combat; shotguns, high damage at close range; sniper rifles, precision weapons for long-distance kills; explosives, grenades, rocket launchers, and mains for area damage. Example: Destiny 2. White matters, a diverse arsenal allows players to adapt their strategy to different scenarios. Cover systems. Cover systems let players use the environment to shield themselves from enemy fire. How it works? Players can crouch behind objects or walls to avoid damage. Some games include dynamic cover systems, allowing players to peek or shoot from behind cover. Destructible environments add tension, forcing players to relocate. Example: PUBG. White matters, using cover effectively is critical for survival and tactical gameplay. Adds, aim down sights. Adds or aiming down sights provides greater accuracy at the cost of mobility. How it works? Players can switch from hip firing to a scope or zoomed in view. Adds often slows movement but reduces weapon spread. Some weapons, like snipers, rely heavily on this mechanic for precision. Example: Call of Duty. White matters, adds realism and rewards players who prioritize accuracy over speed. Kill strikers and perks. Kill strikers and perks reward skilled players with powerful bonuses or abilities. How it works? Key strikers reward like UAVs, airstrikers, or additional ammo for conservative kills. Perks, passive abilities that enhance speed, damage resistance, or weapon handling. Example, Overwatch. White matters, these mechanics encourage skillful play and reward high-performing players. Multiplayer communication. Effective communication is essential in team-based FPS games. How it works? Voice chat and pin systems allow players to coordinate tactics, marking enemies, objectives, or supplies, ensuring better teamwork. Some games include quick commands like need backup or enemy spotted. Example, Counter-Strike. White matters, communication evaluates team strategy, making multiplayer games more engaging and cooperative. Environmental interaction. Environmental interaction adds depth to gameplay by making the world itself a tactical element. How it works? Players can trigger traps, open doors, or interact with destructible elements. Dynamic weather or lighting changes affect visibility in tactics. Some maps include vehicles or stationary weapons. Example, Apex Legends, map changes. Why it matters? Interactive environments keep matches unpredictable and exciting. Resolution. Resolution defines the canvas size of pixel art, determining how many pixels make up the image. Key features: common resolution include 16 by 16, 32 by 32, or 64 by 64 grids. Smaller resolution emphasize simplicity, while large ones allow for more detail. Game resolution must align with the described retro aesthetic or modern approach. Example, City East uses 16 by 16 sprites for its charming characters, balancing detail and simplicity. Why it matters? Resolution sets the stage for the level of detail and style your pixel art will achieve. Perfect pixel. Perfect pixel art ensures every pixel is placed intentionally, avoiding blurry or inconsistent visuals. How it works? Art is created and scaled with anti-aliasing, preserving sharp edges. Tools like grid, snapping help maintain clean lines. Example, Shovel Knight demonstrate pixel-perfect art with crisp, retro-inspired visuals. Why it matters? Clarity and precision are essential in making pixel art visual appealing and authentic. Color plates. Pixel art often uses limited color plates to evocate a retro aesthetic and maintain consistency. How it works? Artists select a small number of colors, often 8, 16, or 32 shades. Colors are chosen to balance contrast and harmony. Some games use iconic plates like the NES's 56 color limit. Example, Hyperlight Drifter uses a bold, limited plate to create a striking and cohesive world. Why it matters? A strong plate defines the mood and style of pixel art, making it instantly recognizable. Anti-aliasing. Anti-aliasing smooths judge edges in pixel art by blending colors along the edges. How it works? Additional pixels are shaded in between hard edges to create the illusion of smoothness. Works best in higher resolution pixel art to maintain sharpness. Example, Octopath Traveler uses sub-anti-aliasing to blend pixel art into its 3D environments. Why it matters? Anti-aliasing adds polish to pixel art, especially in modern games blending styles. Tethering. Tethering creates texture and shading in pixel art by alternating two or more colors. How it works? Patterns like checkboards or gradients are used to transition between colors, commonly used in areas with limited color plates. Example, Metal Slug uses tethering for realistic shadows and textures in its environments. Why it matters? Tethering enhances depth and detail without increasing the color count. Sprite animation. Animating sprites bring pixel art to life through frame-by-frame motion. How it works? Each frame represents a single movement, like walking or attacking. Smooth animation use more frames, while retro styles often use fewer for charm. Example, Halo Knight features fluid sprite animations that add character to its protagonists and enemies. Why it matters? Good animations make characters and environments feel dynamic and alive. Tile-based design. Tile-based design involves creating small, reusable tiles to build game environments. How it works? Tiles are designed in a grid, often 16 by 16 or 32 by 32. Reusing tiles creates cohesive and efficient level designs. Example, Strawda Valley uses tile-based art for its vibrant, detailed farm environments. Why it matters? Tiles streamline the creation of large, complex world while maintaining visual consistency. Outlines. Outlines enhance pixel art by defining shapes and separating elements. How it works? Black or dark colored outlines create bold, cartoonish visuals. Colored outlines blend characters into their environments for a cohesive look. Example, Undertale uses blood outlines for its charming character designs. Why it matters? Outlines make characters and objects stand out, improving readability and style. Lightning and shadows. Lightning and shadows add depth and mood to pixel art, mimic real-world effects. How it works? Highlights and shadows are created with lighter and darker shades of the base color. Techniques like rim lighting or global illumination simulate realistic light sources. Example, Dead Cells uses dynamic lighting to enhance its dark, atmospheric environments. Why it matters? Lighting transforms flat pixel art into dynamic, immersive visuals. Parallax scrolling. Parallax scrolling creates the illusion of depth by moving background layers at different speeds. How it works? Foreground elements move faster than the background elements as the player moves, adds a 3D effect to 2D environments. Example, Celeste uses parallax scrolling to make its mountain landscape feel vast and alive. Why it matters? Parallax scrolling adds a sense of scale and immersion to pixel art games. Finite state machines, FSM. Finite state machines are one of the most common methods for controlling NPC behavior. How it works? NPCs operate in predefined states like idle, patrol, attack, or flee. Transition rules dictate when an NPC moves from one state to another. Example, an enemy patrols until it sees the player, then switches to attack mode. Example, The Legend of Zelda. Why it matters? FSMs are simple, yet effective for creating clear, predictable NPC behaviors. Behavior trees. Behavior trees allow for more flexible and modular NPC decision making. How it works? Behaviors are arranged in hierarchical tree structure. NPCs evaluate nodes in the tree to decide actions based on priority and conditions. Example, a guard might prioritize chasing the player over investigating a noise if the player is inside. Example, The Last of Us Part 2. Why it matters? Behavior trees make NPCs feel smarter and more responsive to dynamic situations. Pathfinding systems. Pathfinding ensures NPCs can navigate the game world intelligently. How it works? Algorithms like A* calculate the shortest path around obstacles to reach a target. Dynamic pathfinding adapts to changes in the environment, like blocked routes. Example, a shopkeeper in an RPG walking to a specific store while avoiding obstacles. Example, Skyrim. Why it matters? Pathfinding makes NPC more realistic, preventing awkward collisions or erratic behaviors. Scripting systems. Scripting defines fixed sequences of actions or dialogues for NPCs. How it works? NPCs follow pre-written scripts triggered by player actions or environmental events. Example, an NPC in Red Dead Redemption 2 greets the player differently based on past interactions. Example, Red Dead Redemption 2. Why it matters? Scripting allows for detailed and personalized NPC behaviors, enhancing storytelling. Rule-based systems. Rule-based systems rely on sets of if-then rules to govern NPC behavior. How it works? Example, if health is low, then flee. Rules can be layered for complex decision-making. Example, Age of Empires. Why it matters? These systems are straightforward and effective for NPCs with specific rules or tasks. Utility systems. Utility systems score possible actions based on importance, allowing NPCs to make rational choices. How it works? NPCs evaluate multiple options like attacking, healing, or fleeing and choose the one with the highest score. Scores are dynamic, adjusting based on the situation. Example, The Sims. White matters, utility systems make NPCs feel thoughtful and adaptive to player actions. Emotional AI. Emotional AI gives NPCs simulated feelings that influence their actions. How it works? Emotional states like fear, anger, or happiness affect behavior. Example, a frightened NPC might avoid the player, while an angry one attacks. Example, Detroit become a human. White matters, emotional AI adds depth and realism to NPC interactions, making them feel more relatable. Crowd systems. Crowd systems manage large groups of NPCs, ensuring realistic group behavior. How it works? NPCs follow basic rules like flocking, disappearing, or avoiding collisions. Example, a bustling city in Assassin's Creed where NPCs react to the player's action. Example, Watch Dogs. White matters, crowded systems create immersive environments filled with believable NPC interactions. Learning AI. Some NPCs using learning algorithms to adapt their behavior over time. How it works? Machine learning allows NPCs to analyze player actions and adjust accordingly. Example, enemies in Middle-earth, Shadow of Mordor, remembering past encounters and adapting strategies. Example, No Man's Sky. White matters, learning AIs makes NPCs unpredictable and challenging, enhancing replayability. Procedural NPCs. Procedural systems generate NPCs with unique traits, appearances, and behaviors. How it works? Algorithms create diverse NPCs on the fly, populating worlds dynamically. Example, randomly generated townsfolk indoor fortress. Example, Cyberpunk 2077. White matters, procedural NPCs add variety and depth to game worlds without requiring manual design. Level of detail, LOD. Level of detail, or LOD, reduces the complexity of objects as they move further away from the camera. How it works? Developers create multiple versions of the same object with varying levels of detail. High detail models are used for close-ups, while simplified versions appear at a distance. This reduces rendering load without sacrificing visual quality. Example, The Witcher 3. White matters, LOD ensures games look great while maintaining smooth performance, especially in open-world environments. Culling. Culling prevents the rendering of objects that aren't visible to the player. How it works? Frustum culling. Only objects within the camera's field of view are rendered. Occlusion culling. Objects blocked by other objects aren't drawn. Backface culling. Surfaces facing away from the camera are ignored. Example, Horizon Zero Dawn. White matters, culling saves processing power by forcing only what the player sees. Textual streaming. Textual streaming dynamically loads textures based on the player's proximity and viewpoint. How it works? High-resolution textures are loaded only when needed, reducing memory usage. Unused textures are unloaded in the background. Example, Call of Duty Warzone. White matters, this technique balances visual fidelity with performance, especially in large, detailed environments. Baked lighting. Baked lighting pre-calculates light interactions and stores them in textures, avoiding real-time calculations. How it works? Lighting for static objects is baked during development. Dynamic lighting is used sparingly for moving objects or characters. Example, Uncharted 4. White matters, baked lighting achieves realistic visuals without overloading the GPU. Mesh instancing. Mesh instancing reuses the same geometry for identical objects, like trees or rocks, to reduce memory usage. How it works? Instead of creating multiple copies of an object, the engine renders one instant multiple times. Position, rotation, and scaling are adjusted to avoid repetition. Example, Minecraft. White matters, instancing reduces memory overhead and improves rendering efficiency. Resolution scaling. Resolution scaling dynamically adjusts the game's resolution to maintain constant frame rates. How it works? The sim renders at a lower resolution during instant scenes and scales up to match the display resolution. Techniques like NVIDIA's DLSS or AMD's FSR are use AI to upscale the image. Example, Cyberpunk 2077. What matters? Resolution scaling ensures smooth gameplay without compromising too much on visual quality. Physics optimization. Physics systems are optimized to calculate interactions only when necessary. How it works? Simplified physics simulations are used for background objects. High-detailed physics are reserved for critical gameplay elements. Rigid body physics or particle systems are optimized for real-time performance. Example, Half-Life 2. White matters? Efficient physics keeps gameplay smooth while maintaining realistic interactions. Dynamic LOD and asset streaming. Dynamic LOD adjusts not just models but also textures and effects based on in-game activity. How it works? Textures, shaders, and particle effects adapt to the player's approximately or focus. Dynamic systems ensures high fidelity during critical moments and scale down in less demanding scenes. Example, Red Dead Redemption 2. What matters? Dynamic systems provide a seamless experience while conserving resources. AI optimization. NPC behavior and pathfinding are optimized to avoid unnecessary calculations. How it works? Idle NPCs or distant enemies use simplified AI states. Pathfinding systems use grid-based or hierarchical methods to reduce processing. Example, Halo. What matters? Efficient AI ensures large worlds feel alive without compromising performance. Memory management. Proper memory management prevents performance drops or crashes. How it works? Garbage collection removes unused data from memory. Objects pooling reuses resources like projectiles or particles. Example, Unity and an Unreal Engine-based projects. What matters? Good memory management ensures constant performance, especially in resources-heavy games. Paper prototyping. Paper prototyping is one of the simplest and fastest ways to test game ideas without writing any code. How it works? Developers use paper, marks, and other physical materials to sketch out game mechanics, levels, or UI layouts. Players or developers simulate gameplay by moving pieces and acting out actions. Example, designing board games or card games, planning level layouts for platformers or puzzle games. What matters? Paper prototyping is cost-effective and helps quickly identify design flaws before moving to digital tools. Grayboxing, blockouts. Grayboxing involves creating a basic, untextured version of the game environments to test layout and functionality. How it works? Developers use placeholder assets to represent characters, objects, and terrain. Focus is on gameplay flow, scale, and spatial awareness rather than visuals. Example, testing platformer level layouts in Super Mario Maker, evaluating combat arenas in FPS games like Halo. What matters? Grayboxing ensures the game structure and pacing work before investing in detailed assets. Visual scripting prototypes. Tools like Unity's plot or Unreal Engine's blueprints allow developers to create prototype mechanics without coding. How it works? Drag and drop nodes represent game logic, such as triggers, movement, or animations. Developers connect these nodes to create interactive gameplay elements. Example, prototyping enemy AI behavior, testing platforming mechanics like double jumps or wall climbs. What matters? Visual scripting makes prototyping accessible even for non-programmers, speeding up the iteration process. Role-playing, analog playtests. Role-playing prototypes involve acting out gameplay scenarios in real life to test mechanics and player interaction. How it works? Participants simulate game mechanics, often using dice, card, or verbal instructions, used for testing mechanics like stealth, decision-making, or turn-based combat. Example, designing RPG mechanics before coding, planning branching narratives for story-driven games. What matters? Role-playing helps refine complex systems and mechanics in a collaborative, hands-on way. Digital prototypes. Digital prototypes are basic versions of the game built using game engines or custom tools. How it works? Developers create playable builds that include placeholder graphics and simplified mechanics. Focus is on core gameplay systems such as movement or combat. Example, early builds of CDs to test platforming mechanics, prototyping crafting systems for games like Minecraft. Why it matters? Digital prototypes allow developers to test and refine mechanics in a format closer to the final product. Paper doll prototyping. Paper doll prototyping is often used for character customizations or UI testing. How it works? Paper cutouts represent characters or interfaces. Players swap pieces to explore customization options or interact with menus. Example, designing character outfits for RPGs like The Sims, testing inventory system for survivor games. What matters? This method ensures usability and player satisfaction with interface design and customization options. Code-based prototyping. Code-based prototypes involve writing scripts to test specific mechanics or systems. How it works? Programmers create scripts that simulate core gameplay such as physics, AI, or interaction. These prototypes often focus on isolated mechanics rather than full gameplay. Example, testing grappling hook mechanics for action games, simulating AI pathfinding for NPCs. Why it matters? Code-based prototypes validate technical feasibility and help refine gameplay details. One mechanic prototypes. Sometimes developers focus entirely on a single mechanic to perfect its implementation. How it works? A prototype is built around one mechanic, like jumping, shooting, or crafting. Developers test variations to optimize the responsiveness, timing, and feedback. Example, refine the whip swings mechanics in Spider-Man, testing sword combat for games like Dark Souls. Why it matters? Focusing on one mechanic ensures it feels polished and satisfying before integrating it into the full game. Procedural prototyping. Procedural prototyping tests systems that generate game content algorithmically. How it works? Developers create algorithms to generate levels, characters, or quests. Prototypes explore how randomness impacts gameplay and balance. Example, testing procedural generated dungeons in Haze, experimenting with planets generation in No Man's Sky. Why it matters? This method ensures procedural systems produce diverse, engaging content. VR and AR prototyping. For VR and AR games, prototyping involves testing special interactions and player immersion. How it works? Developers use VR or AR tools to create interactive experiences. Focus is on player comfort, intuitive controls, and spatial awareness. Example, designing hand tracking mechanics for Half-Life Alyx. Prototyping AR interactions for mobile games. What matters? Prototyping in VR and AR ensures the experience is immersive and user-friendly. Sliding puzzles. Sliding puzzles involve moving pieces to arrange them into a specific pattern or position. How it works? Players move tiles often restricted by limited empty spaces to solve the puzzle. Variations include numerical sequences or image restrictions. Example, Uncharted sliding tile puzzles. Why it matters? Sliding puzzle challenge spatial reasoning and strategic planning. Match 3 mechanics. Match 3 games are among the most popular puzzle mechanics, focusing on aligning similar elements. How it works? Players swap adjacent pieces to create rows or columns of 3 or more matching items. Matches triggers effects like cleaning blocks or cascading combos. Example, Candy Crush Saga. Why it matters? This mechanics is simple, addictive, and visually satisfying, making it a casual favorite. Physics-based puzzles. Physics puzzles simulate realistic interactions, requiring players to manipulate objects to solve challenges. How it works? Mechanics like gravity, momentum, or balance play a key role. Players push, pull, or drop objects to trigger desired effects. Example, Portal. What matters? Physics puzzles add dynamic and tactical interactions, creating immersive problem solving. Pattern recognition. Pattern recognition puzzles require players to identify and replicate sequences or arrangement. How it works? Players analyze symbols, colors, or shapes to discern patterns, often used in memory or rhythm-based games. Example, The Witness. Why it matters? These puzzles sharpen observation and analytical skills. Logic puzzles. Logic puzzles demand reasoning to solve problems using rules and constraints. How it works? Players deduce solutions based on given information and logical relationships. Common examples include Sudoku or grid-based deduction puzzles. Example, Hexails. White matters, logic puzzles engage critical thinking and provide immersed satisfactions upon solving. Escape room mechanics. Escape room mechanics combine various puzzle types into a cohesive challenge, often with a narrative. How it works? Players solve interconnected puzzles to process through a room or series of rooms. Clues are often hidden in the environment, requiring exploration and deduction. Example, the room. White matters, these puzzles blend creativity and storytelling, offering immersive, multiple-layered experiences. Word puzzles. Word puzzles challenge players with anagrams, crossroads, or vocabulary-based tasks. How it works? Players form words from given letters or solve riddles, often used in mobile games or educational contexts. Example, word spaces. White matters, word puzzles improve language skills and encourage creative problem solving. Sequence and timing puzzles. These puzzles involve activating elements in the correct order or within a time limit. How it works? Players experiment to find the correct sequence of actions. Timing puzzles add pressure by requiring precise execution. Example, braid. White matters? These puzzles challenge memory, coordination, and timing. Code breaking. Code breaking puzzles require players decipher hidden messages or solve ciphers. How it works? Players analyze patterns, symbols, or numbers to deduce codes, often paired with narrative elements or mystery themes. Example, keep talking and nobody explodes. White matters, code-breaking puzzles combine logic with creativity, offering rewarding challenges. Resource management puzzles. These puzzles challenge players to allocate limited resources efficiently. How it works? Players balance constraints like time, energy, or materials to achieve goals, often overlaps with strategy games. Example, Mini Metro. White matters, resource management puzzles encourage planning and strategic thinking. Watch this video to discover NPC behavior systems you need to know as a game developer.